Uh, okay, okay. Hello, everyone. Welcome you to the SmartMed academic seminar. Today is really our great honor to have Professor Nicholas A. Kotov here to give us a talk. Before that, please allow me to introduce Nick first. So, Dr. Nicholas A. Kotov is a Irvin Namir Distinguished Professor of Chemical Science and Engineering at the UMesh. That is a very top university in US. And Lake is known for the fundamental discoveries in biomimetic nanostructure and interface-based materials engineering. He demonstrated that the ability to self-organize into complex structure on interfaces or in liquid media is unifying the property of all nanostructures. Lake recreated the universal process by which complex biological structures are assembled and uncovered the pathway that nature used to create these materials. With this insight, it designed and implemented a versatile family of composite materials for various chemical engineering processes from gas separation to charge transport with extraordinary property that had previously been deemed unattainable. So Lake's research methodologies have seen widespread adoption by researchers and industries. So Lake is also the founder of several startup companies that commercialize bio-inspired nanomaterials for different technologies. So today is really our great honor to have him here to share with us a story entitled Biomimetic Nanocomposite and Related Technologies. Without further ado, Nick, so our floor is yours.
Thank you very much, Professor Junchen. It's my honor to be a part of this webinar, and I appreciate very much all the participants who have joined. I'd like to talk to you today about the work that is very close and dear to my heart, which I started actually when I was a student. It evolved since then, and the title of today's talks and the topic will be the biomimetic nanocomposites. And I think what I'd like to emphasize in this talk is how we can engineer by self-organization a very complex material, and what would be the functionalities which are needed from these materials. Because if they are complex, they need to serve something. They need to be useful. And I will also show how it can be done by using the experimental means as well as by computational means, including the new ones by using the graph theory. So if we need to motivate this topic, I recently came across these numbers which stunned me. I wouldn't expect that biomimetic materials are already a big industry. In 2020, they grossed across the world 20 billions. And among them, the biomimetic nanocomposites, which are made from nanoparticles, nanowires, nanoclays, is at least 5 billions. So this means that these are materials which are needed to solve some big problems. And what are they? They can be found in many current and emerging technologies, for instance, the transportation technology, the energy, as well as the biomedical technologies, for instance, the neuroprosthetic implants. And some of the newest type of the technologies, for instance, robotics and machine vision. So altogether, it can be summarized as the need to combine many different properties in one material in the same time. So if it has a record one's property, say conductivity or strength, that's not enough. We actually need to have 2 or 3 or 4 in the same time, and that's when it gets very hard. Because some of the properties are actually contradictory to each other. And we often want to have the properties in the part of their correlation diagram, which is at the moment empty. For instance, we want to have high mechanical properties and low density. Or we would like to look at some other properties, for instance, the thermal conductivity and electrical conductivity. And still, this part and that part are actually empty even now, despite lots of effort that have been done in this area for 100 years. So how to design the materials for these combinations? So actually this comes from learning from nature, and one of the classical examples is nacre, which combines very high toughness, very high stiffness, and it actually combines low density. In our metrics, we also need to add there that in order to make it, we actually have very little expenditures of energy compared to, for instance, plastic or steel. This is done at room temperature at under very simple conditions. So why does nacre has these unique properties? The idea is that this kind of materials have these properties because of the periodic organization of soft and hard faces. In this case, these are inorganic materials and organic materials. I also would like to point out that this kind of organization of the material has a pattern. And in this case, it's actually a fairly simple pattern. And later we'll find some of the complex patterns. Also, one of the key findings of the research for the last 20 years is that not only this organization, but also interfaces in between the soft and hard faces play a big role. How do we replicate it? Actually, this can be done fairly simple way. In fact, by using self-organization and room temperature, and many conditions are very much alike to what the nacre is using in the nature. We have produced it from a number of materials by using nowadays classical method of layer-by-layer assembly, which have been developed by Gerard Becher. We designed this method in order to make the biomimetic composite materials. We started actually not from clay, but from graphite oxide. And in all the cases, we have very high contribution of interfaces and layered organization of organic and inorganic matter. The advantage of LBL is that the organization is very accurate and the uniformity is high, which enables us to establish the physics and chemistry of these interfaces. So we can make it from a variety of materials, for instance, graphite oxide or carbon nanotubes, or other people have done it from cellulose or gold nanoplates. So there are many types of nanometer scale materials which can be organized in nacre-like structures in this layered composites. And in all the cases, inevitably and surprisingly, or not, they reveal a very unique combination of the density and Young's modulus. And that's actually, looking back, is not surprising because the contribution of interfaces and the mechanisms that are operational in nacre and in these materials are exactly the same. So, in fact, we can not only obtain the combinations which are in nacre, but much better. We can also look at Winterman diagram, which relates thermal conductivity and electrical conductivity, and this is the same. So all of the repaired materials from boron nitride platelets or from the fin or from others, they all lay or fall into these empty areas of the classical material and the classical so with that knowledge, we can also establish some of the computational means. And I think this work by Marcus Builder at MIT, it demonstrates very well that LBL assembly from graphene oxide and PDDA is very simple and very conducive to the computational description because each layer, each interface is reaching the equilibrium, and that leads to exceptional cohesion at each interface, and thus to the review prepared by Professor Guo from Beihang summarized very nicely a number of applications of this kind of materials from, say, energy to fire retardant to gas barriers and to the transportation. One simple example so that you could connect to this market report and large amount of investment that have been made over this year. So, for instance, even simple, the gas barrier layers, which made in nacre-like fashion in these nanoscale layers of clay, or some other materials. It's commercially used and is used in many packaging. In fact, if you go to supermarket and to take some Nestle chocolate and do the cross section, that will be very similar transmission microscopy. But interfaces offer something more. And this kind of biomimetic composites also offer more complex organizational toolbox. For example, we not only can organize highly anisotropic particles, for instance, clay, but also seemingly round particles or isotropic particles, for example, gold. And that has a lot of utility because if we can organize them, for instance, in chains, that would lead to interesting electrical and optical properties. And initially, we started with electrical properties. It was done in collaboration with my good colleague at University of Michigan, Tirad Uher, and we decided to assemble gold nanoparticles in layer-by-layer fashion in order so that we allow gold particles to assemble at each interface into the chains. And this resulted immediately in something quite unique. The conductivity of these composites were extremely high. In fact, if we look at the comparison with some of the vacuum-assisted filtration composites, so when you take, say, some nanoparticles, gold or clay or graphene, and under vacuum, you compress them on the filter. Let's say in this case, that organization, that gradual organization build-up of the layers results in much higher electron transport. In fact, we can compete not only with some composites, but also with some metals. In fact, the conductivity of these composites is actually higher than some of the icons in materials, which is dot, and conductivity, interestingly enough, is higher than in mercury. If we look at some other applications, we can also start being interested how the organization at interfaces changes optical properties. And this would lead us eventually to the machine vision and chiral structures, which I talked last time. I will not talk about it today, except when it covers the composites. So we did exactly the same thing. So we deposited gold nanoparticles at the interfaces, but in this case, we initially twisted the substrate. So one advantage of this technique that it can deposit particles at surfaces of any curvature. Could be actually deposited at nanoparticles. And after the deposition, we let the PDMS substrate to relax and observed quite interesting opalescence. So immediately it means that in these surfaces, we have some periodic structure. We started looking at bioatomic force microscopy and saw actually two levels of organization. First, we have the wrinkles, which are not absolutely organized as in the work of Andreas Ferry, but they have their periodicity. What's even more important for the optical properties that the nanoparticles here are organized into the chains. And these chains have three-dimensional structure. And if we look at the mirror, for instance, here, these chains become mirror asymmetric or chiral. And for that reason, these composite materials, they acquire a strong polarization rotation. So as you can see, the circular dichroism peaks here are at the plasmonic region of gold nanoparticles, and therefore they correspond to the gold chains and the plasmonic resonances in them. We looked at both peaks here at 600 and 550, and they have several contributions. Some of them are actually um, have the contributions of linear ichroism. But this peak at 550 has very strong contribution of circular ichroism. And that's exactly because of the chirality of the system. These composites are flexible. These are the combination of properties that we were interested in. And their advantage over some other materials is that one can stretch them and change the intensity of the polarization rotation. So it becomes a mechanically modulated structure which can rotate the polarization rotation of light in a very high range of values. So this occurs because when we stretch, we actually compress in the middle, and for that reason, the S shape of the chain, so the protrusions in the normal directions are increasing, and that's why the polarization is increasing. And we can do it many, many times, and that becomes a modulated polarization rotation. So as you can see here, we can do it over the 10,000 cycles without any change of optical properties. Not only that, but we can also do it with some other materials, for instance, carbon nanotubes. In this case, we chose metallic carbon nanotubes, which are also plasmonic, but in infrared. So they have a peak in UV, they have a peak in visible, and they have that very useful peak in the near infrared, about 1,000 nanometers. Useful for a number of reasons, and biomedical reasons are one of those. The modulation here still works, and this is identical to the mechanism that you saw with gold nano. One of the interesting capabilities which emerged, and the questions that we put forward at some of the meetings of composite community, what if we can make a thermodynamically unfavorable organization of the interface? So we try to organize always, or it's actually easy to organize the platelets which are absorbed flatly at the interfaces. This is the natural minimum of delta G, but there are a number of mechanical properties which emerge if we form the regional-like structures. In respect to the biology, they actually emerge across a variety of species in enamel of teeth. We have such organization of enamel, so we have the vertical organization of the solid face and then soft face oriented in this way, or in octopus or in walruses, and even in many other species, including the dinosaurs. So it's not accidental. And we decided to replicate it. And in order to attain this kind of unfavorable organization of the interfaces, we used the method of the growth of zinc oxide wires perpendicularly to the interface. And after that, we used LBL to deposit the soft matrix in between very conformally. And one can repeat that growth, deposition, growth, deposition as many times as we want, obtaining in this way a very accurate and uniform replica of columnar phase in M. After that, one can investigate their mechanical properties, and you can appreciate that this process can also be used to make the samples at macro scale. And we started looking at stiffness and strength and toughness, the unusual combination of properties which this organization of interfaces and soft and hard components, it turns out that it shows in the combination of viscoelastic properties. So it's actually quite stiff. It's enamel, so it needs to crack nuts and bones. But in the same time, it has a high value of tan delta or viscoelastic efficient, the ability to dissipate the vibrations. And these materials are also quite light, so you don't need to use, for instance, very heavy metals, I mean, for instance, like this. And just by playing with organization, you can obtain very unusual and record type of combinations of lightness, stiffness, and ability to damp the vibrations. I promise you to address how these materials can be designed, and indeed, this work shown that interfaces are the key in the understanding how these materials are actually operating. By using molecular dynamics in collaboration with Anthony Vaz, Elena Ruda, Naida Lesevich, and Trisha Sain, we modeled the stress propagation through the stiff zinc oxide rods. And it turns out that there is a very efficient translation of stress if the interface is organized in that way. And if we model, say, the mechanical properties here, then we have a virtually complete match with experimental data. And that indicates very clearly that by modeling interfaces, for instance, by molecular dynamics, now there are other techniques which can be used here, we can arrive to the predicted set of properties. And LBL is essential here because it actually gives the equilibrium structure of polymer at the interface. All right, so this was all very nice nacre-like structures, but there are quite unique materials which are not nacre. And some of them we maybe underestimate until we lose them. And this is cartilage, as well as other materials which we have in our body based on nanometer scale fibers of convective tissue. So in this case, these are stiff fibers from collagen, and they're wrapped with a soft amorphous or assumed to be amorphous phase, and all together this creates a very unique combination of mechanical properties, of biological properties, and transport or some ion conductive properties. I'd like to point out that in this case, we already have a fairly complex motif, which is not a periodic structure as in nickel. But the role of interfaces is still humongous. We decided to replicate cartilage by using a different type of material, actually from Kevlar. It's a recycled Kevlar. It can be converted from old Kevlar tarps and some other materials by simple solution in CMSO. And in this case, we form aramid nanofibers, and there are now many people who are working and doing fantastic work in this area. I was actually stunned how many interesting and unique materials, including 3D printing, are done now by using this and similar kind of aramid fibers. One of the unique properties of these fibers made in this way is that they're borage, so they are entangled very easily, and also they can be wrapped with soft polymers also quite easily. And as you can see, indeed, they form this entangled complex network structure, which resembles cartilage. Initially, we looked at the commonalities in structure and in physical properties. And one of the interesting points that cartilage is actually made of a lot of water. 92% of that fairly stiff material is water. And these nanofibers are able to transfer enormous amount of stress over many years. The organization is quite unique and need to be replicated and understood better. So we tested the mechanical properties in order to see if we can match cartilage. Not only we can match cartilage, we can actually make a better cartilage-like materials, just like with an nickel. These materials can be used in a variety of technologies. I would like to show you some of our results for energy, for batteries. And the first data were obtained by aramid nanofibers made by our favorite technique, LBL. And we learned that these stiff, conformal, insulating, ion transporting layers can actually prevent the growth of very stiff metallic dendrite. Not only lithium, which is fairly soft, but also copper and zinc. And only a few LBL layers is enough in order to suppress completely the growth of the dendrites. And this is done at fairly high C, so it's not gentle growth, it's actually aggressive. And the number of layers is not that big. The thickness is about 500 nanometers. If you compare it with the standard thickness of separators in lithium batteries, it's actually 25 microns. The diagrams that we can create here also indicate that these composites fall into some of the poorly populated part of the combination of property charts, for instance, the ion transport, which is described by internal resistance and stiffness. This is needed in order to allow ions to go through. This is needed to suppress the dendrites. We could also add here the third axis, and if we add that, then it will be very clearly that we are entering in the new empty zone in the new window in respect to toughness, a very important material for flexible batteries as well as for the implants. We started looking not only at lithium batteries, but also zinc. And if you follow that literature, it's some of the most favorite batteries right now because zinc is quite inexpensive. And zinc air batteries have quite unique combination of gravimetric energy and volumetric energy. But the dendrites are tough there. And prevention of the growth of zinc dendrites is much harder than for lithium because it's harder, and also the electrolytes that are used in zinc, they're actually not allowing two valent ion of zinc to transport fast. So the charging is not that fast. So we decided that we need to try this challenge, and we were able to address it. Here we used a combination of aramid nanofibers, also made cartilage-like structure, quite thin. It is 3 microns. It's also porous, thin, and uniform. In this case, it was with polyethylene oxide. We made the classical zinc anode with manganese oxide, not the best cathode, but it'll enable us to show the proof of concept. And indeed, we saw that if we don't use our separators, the dendrites are growing very rapidly. But if we use them, then we don't have almost any dendrites at all, which can also be observed on the electrochemical data. The batteries remain flexible and can be corrugated after the preparation of the battery, so they're safe. And in order to demonstrate their unique capabilities, we also integrated them as structural batteries. So this is not just a battery, it actually carries some load and serves as the protection for electronics for the drones. Now, if we look at the transportation area, the extension of the range for the drones is some of the big problems which slowing down the development of, say, air taxi using the drones. And we successfully launched it, and it was a lot of fun, actually. So we got this structural battery working, and we started looking at the fundamental aspects of this network. One thing that I promised you is that we need to look at how we can design these materials better. And with Nacre, it's easier. We can use the organizational aspect, I mean the regularity of the layer. In this case, the network is irregular. And that led us to the idea of using graph theory or the network theory. I talked a little bit about it last time in terms of complexity, but in this case, it's actually about the properties. So we described this network of nanofibers by using the same formulas as we used in the paper about complexity and plurality, and the basic idea is quite simple. So if we have a two-dimensional rod-like structure, it will be a K2 graph. And after that, the junction automatically becomes the node. And after that, we can apply the network theory or graph theory to describe the organization of this network by using a variety of indices, for instance, average clustering coefficient or average model connectivity. All of them are describing some aspect of the structure. It may be short range or long range. Importantly, that it changes from the composite to composite and from network to network. So this is organization of collagen fibers in actual cartilage. This is our aramid nanofibers. We have a differences in scale, but importance here is actually organization of the fibers. And also, for comparison, we looked at the network from gold nanowires. We used the computational tool to extract the graph theoretical representation of these composites from SEM images called structural GT. And after that, we can analyze that graph, compare it to aramid nanofibers and to gold nanofibers. Very interesting that I was very happy to see that and not expecting too much. It turns out that cartilage and NNF share the structural indexes which almost overlap each other. In the same time, they are not the same as the networks which are made by gold nanowires. They may be better for something else, for instance, for conductivity, but they have a different long-range order and short-range order, while the cartilage and NF are almost identical. And that proven the fact that the cartilage and NF do have the same organization. We can look at it and say, it may be the same. But here it's actually mathematically confirmed that it is true. And we applied it to a number of design problems for materials. One of them are implantable devices. There are, of course, a lot of wearable and biomedical devices which needs to be worn for quite a long time. And in all cases, one of the key things which fail is actually insulating them. Not electrodes, not electronics, but these insulating layers which coat all that. And we started looking how can we improve it. it turns out that our NF cartilage-like material can it shows very strong adhesion, flexibility, and toughness. And these three properties, combined, of course, with electrical insulating nature of epoxy and a composite, enables it to be excellent insulator and adhere to the substrate much better than the competitors, for instance, really. The other thing is that nanofibers, which originated from the organization of the cartilage and other connecting tissue, it's actually the nanofibers from ECM, from extracellular matrix. Their geometry, their stiffness here is retained, and cells sense it. And for that reason, NF composites actually much better for adhesion of the cells. The next thing that we started looking is, again, battery, but in much more complex version. We started looking at structural batteries from zinc, which could be higher charge and have a solid electrolyte. But this required new types or new combination of properties, and by using the correlations of average clustering coefficients and Wiener density, one can see that now with organization of the nanofibers, we can actually choose this would be the average clustering coefficient, and that would be the Young's modulus and toughness. Interestingly enough, the ionic conductivity does not depend very much, so it's almost flat in respect to ACC. So that enables us to vary these parameters and retain another one. It's used, we applied it to demonstrate that we can make biomorphic battery. So it's structural battery, and you and me and all the other animals, we don't have a body part which is battery-like. So we actually store energy all over the body, and that's beneficial. It's actually efficient way to process, store, and distribute weight of the energy stored. And so indeed, we decided to replicate it initially in small bugs like this, and then in a big, or in a bigger robot like that. Important things here is that if in drone we still had a small battery for liftoff, here we don't. So this little dude is powered by exclusively our batteries, which are located just in a few places. And if we look at the area of we can cover, we can actually extend the range and the charge of this robotic toy over 72 times over the normal one. So with this, thank you tremendously. And I would also like to thank this wonderful gang, which suffered quite a bit during last year. It was a hard year, but we're now also getting back to normal, and these are their normal faces, and they are troopers. So thank you all, and I'll be happy to answer any questions that you might have. Thank you so much.
Okay, thank you very much, Nick, for your wonderful talk. So here, I'm as the messenger to pass some of the questions from the audience for you. So one first question that, yeah, one first question that in the biomimetic composite for robotics. So one of the audience asked a question, I mean, can gel electrolyte mechanically strong enough to prevent the formation of the dendrite?
That's exactly the challenge there. And thank you very much for this very good question, because it was definitely hard to attain this kind of stiffness. So we were able to do that because of two main structural features of this cartilage-like composite. First, each nanofiber is actually very strong. They are very interconnected, and when the dendrites start growing, this stress is efficiently distributed over many neighboring fibers. The other piece is that the pore size here is comparable to the size of the dendrite. So if you look at standard separators, the pore size there is actually quite big. So it's 100 nanometers or so. Here it's about 20. And that means that the dendrite cannot choose the least resistance pathway and has to go through the network. So that smallness of the pores enables one to engage the organization of this composite the best way possible. So for zinc batteries and zinc metal anodes, this is most essential. Because as you possibly know, the zinc dendrites are some of the hardest in these energy storage devices, and this is indeed quite difficult to prevent their growth, especially for high discharge rates.
Okay, thank you, Lico. Thank you for your question, for your answering with a lot of details. So here's another question from audience talking about your literature papers, tooth enamel, that's paper. So they found that in that paper, you use zinc oxide, LBL, to form a multi-layered structure. So they are, just this slide. They are asking, so are the interface between each layer are identical or uniform? So how does this interface shows impact on the mechanical property of the final composite structure?
Yeah, again, very precise, very accurate question, right on in the heart of the problem. So LBL has very special property that it covers uniformly the solid surface. So if we look at how the soft matrix, in this case it was water-soluble polyurethane in, say, this part or that part, it will be identical. And that's because the structure of the interface is established not, for instance, by spin coating or by some other external fields, but rather by equilibrium at local interfaces. And this uniformity of the interfacial structure creates uniformity of the stress transfer from these rods, which are compressed, and this compression results in the extension of the stress into the soft metal from the rod, as can be, for instance, observed by the model. So the stress goes inside the soft matrix, and therefore it's very efficiently damping any kind of vibrations. So, for example, it can be seen here that even just a few nanometers inside, you have already very efficient interaction, very efficient dissipation of energy. So with that role of interfaces, you can compress, you can oscillate, but the entire material will respond. And that distribution of stress, that efficient distribution of stress as in enamel, it predicates the longevity of this material. So it turns out that the reason why enamel has such a structure is because many animals who has this columnar organization, they have one set of teeth for a very long time, say the elephants or humans. And the longevity of these organs is critical. So it's not necessarily how super stiff they are, but actually how long they last overall. And that requires damping the vibrations because they create the microwaves. So the longevity is a result of the combination of high stiffness and viscoelasticity and the viscoelastic properties, the damping coefficient one delta, as we can see on this plot. Hope I answered your question.
Okay, yes, with a lot of technical detail, definitely you fully answered the question. Thank you very much. So there are a number of questions out there, but here I wanted to pick up one last one. So some of the audience may be very concerned that because you are a top professor in a top university, and a lot of students want to join your group. So when you are hiring a PhD student or postdoc, so what is the personal characteristic you look at the most?
Yeah, a good question. And certainly I do hire students and postdocs. Normally, I try to meet with the person beforehand, either in person somewhere at the conference. For example, I just recently hired a postdoc in that area whom I met at the conference in France. And he is actually from Shanghai originally. His name is Wen Bin Wu. We had a very nice chat, and I immediately recognized that this person has quite unique vision of the field, and he has good grasp of the problems. And at that time, I didn't have an opening, but with time, I had, and I decided to make him an offer. So I think the personal qualities which would be important for me is to have a in-depth understanding of the problem of composite design, to able to handle math and maybe some modeling. Also good synthetic skills, but also ability maybe to argue, to have your point of view and your vision of what is important and what may be less important, what's new and what's old. So I'm always striving for something which is different, or which is novel, which is answering the problems of humanity. And I think this kind of mindset is important for me in my students and in my postdocs. So I would love to have many people in my group. I not always can afford that.
So basically, that means you have to have a face-to-face conversation with a candidate before you make a decision, right?
I would really, yes, absolutely. So I typically have a couple of interviews with the person over Zoom or in person.
Okay.
Yeah, and I think each interview would last maybe an hour.
1 hour.
And
Oh.
yeah, and we just, yeah, because it's a big investment for me.
Yeah, that's true. Yeah.
Yeah. If each person, each postdoc and student is kind of a big deal. So it's not very easy to find the money, and also I think I like to work with the people who has excitement, who has, yeah, who
So
understand, yeah. And so I'm trying to get from the conversation with this person or with these people, and during the interview, what person is about. I mean, can he or she work independently? Can he or she be the leader in this field in the future? So after he leaves the group or she, so these kind of things I'm trying to understand.
okay. Okay.
Yeah.
Thank you very much. Thank you for your answer. It's really helpful. Yeah. So
My
I think
pleasure.
yeah,
Mhm.
it's really helpful. Yeah. So probably that's much of seminar today. So Professor John is here. Yeah.
Oh, hi,
You
hi,
have
Professor.
something to
Thank you,
add?
Jim.
Hi, Nick. Hi,
Yeah.
Nick. Thanks for your wonderful talk and detailed answer. Yeah, and also welcome to some of your work to Smart Matter again. Yeah, thank you.
I will. I'm getting
Okay.
another paper ready.
Okay.
Okay.
Yeah.